Hello and welcome to the AI Research Roundup. I am Alex, your host. Today is May 11th, 2025. We are looking at a paper titled SWE-smith, Scaling Data for Software Engineering Agents, which appeared on Hugging Face's trending list, published about 11 days ago on April 30th. This research paper introduces a novel pipeline called SWE-smith. It aims to solve a big problem: the shortage of training data for language models, which are AIs that learn from data when teaching them software engineering tasks. SWE-smith automatically generates many such tasks from existing code, along with their needed execution environments, which are setups to run the code. Alright, so this first figure really drives home how SWE-smith tackles that data shortage. On the left, we see a graph where the yellow line, representing SWE-smith, climbs steeply. This shows it generates many more task instances, specific problems for the AI, from more code repositories or collections of code compared to the blue SWE bench line. The right graph then shows that as an AI agent is trained with more of these solution paths or trajectories, its ability to solve tasks measured by its pass at one resolve rate, that is, its success on the first attempt on the SWE bench. Verified benchmark, a standard test, clearly improves. Okay, so building on that idea of generating more data, this next diagram visually walks us through the SWE-smith pipeline. It starts with real code repositories, which include source code and unit tests. These are small tests checking individual code parts. Then, an execution environment is created, often using a Docker file, which is like a recipe for setting up the software. After that, various task generation strategies like procedural modification or PR mirroring, which cleverly reverses actual software updates to create bugs, are employed. These strategies result in new task instances, complete with a bugged patch, that is, code with an intentional error and an issue description. So, looking at this table, we get a detailed breakdown of those task generation strategies. It shows the yield percentage, that is, how often a strategy successfully creates a task that breaks at least one test. It also lists the sheer number of instances, or individual tasks, and the cost to generate each one. For instance, the combine method is really efficient. In total, over 50,000 task instances were generated, showcasing the scale. The table also mentions fail-to-pass tests, or F2P, which indicates how many tests failed, then passed, giving a sense of task complexity. Alright, now this next table really puts SWE-smith's contribution into perspective by comparing it with other existing datasets. We can see SWE-smith provides a substantial 50,000 task instances sourced from 128 different code repositories. And crucially, unlike some datasets that lack them, SWE-smith includes those vital execution environments. What is really striking here is the environment size. Just 295 gigabytes for SWE-smith compared to terabytes for others that also provide these environments. This clearly shows a huge improvement in efficiency. Okay, so after seeing how efficiently SWE-smith produces data, this table demonstrates the impact of that data on model performance. It compares various language models on the SWE benchlight and verified benchmarks, measuring their pass at one resolve rate. We see results for closed weight models, which are proprietary, and open weight models, which are publicly available. Crucially, the SWE agent LM32B, an open weight model fine-tuned on just 5,000 SWE-smith instances, achieves a 40.2% pass rate on the verified test. This is a top-tier performance for open models, really underscoring the quality and effectiveness of the SWE-smith generated training data. Building on that impressive performance, these next two plots explore how training data specifics affect the outcomes. The left graph shows that specializing a model by fine-tuning it, essentially giving it extra training on data from a particular code repository like SymPy, really boosts its success on tasks from that repository. For instance, the SWE agent LM32B model gets much better at SymPy tasks. But this specialization slightly lowers its ability on other general tasks. The right graph then shows that using data from more diverse code repositories, even with the same total training examples, helps the model solve problems better overall. So variety is key. So to wrap things up on SWE-smith, it is clear that both data diversity and specialized training really influence model performance. This whole system, SWE-smith, tackles a critical bottleneck: the scarcity of quality training data for language models, the AI systems we train for complex software engineering tasks. By automatically creating vast amounts of realistic coding problems, SWE-smith boosts how well these language models solve issues, shown by that strong pass at 1 resolve rate, their first try success rate, and also democratizes research with efficient, open-source tools. That is all for this AI Research Roundup. Thanks for tuning in.